Good morning. My name is Michael Ray. I am science writer here with SENS Research Foundation, and I'm joined this morning by Dr. Abdelhadi Rebbaa, who is the director of our SEM project here at SENS Research Foundation and our research center. Dr. Rebbaa, good morning.
Good morning. Thank you for having me.
So, what's the big problem you're trying to solve?
What we want to try to achieve here is to try to delay the aging process. And we are trying to target it. Basically, we want to target the damage that accumulates in our body with time. As you know, over time, throughout our life, we are exposed to a variety of stressors. Some of them are exogenous, some are endogenous. And as you can imagine, even the metabolism or even the air we breathe, it causes some oxidative stress and can damage our cells. Fortunately, some of our cells can repair this damage, can remove it, but some others cannot because our tissues are heterogeneous, so there's different cell populations. And the cells that cannot remove the damage, they accumulate it and they tend themselves to accumulate with time as we age because they are resistant to that. So our goal is to try to target these damaged cells and remove them, or at least reduce their harmful effect. And the way we are trying to do that is to target them with using senolytics, which are molecules that can selectively kill senescent cells. The other way to do it is using mesenchymal stem cell transplantation. The goal here is to basically to try to either try to replace senescent cells or damaged cells, or use these cells to secrete molecules that will interfere with the harmful effect of senescent cells. So, and then, of course, we will do the combination of the two. Hopefully, that will be even more effective.
Right. So it's a 1-2 punch. You are both removing the cells and you're reducing the harm and potentially reducing the generation of other cells as you go along.
Exactly. Yes.
Yeah. So it's a good combination. All right. So you're using these two approaches. Let's first talk about senolytic drugs. These are drugs that a lot of our listeners will have heard about. They destroy senescent cells. But you are using a next generation of senolytic drugs. Talk to us about that.
You're right. Yeah, the first generation. The problem with it is you need only you need a target that is expressed only in senescent cells, and you senolytic should in theory kill senescent cells selectively compared to non-senescent cells. However, based only on one target, some healthy cells also express the target, and it is a case, for instance, for navitoclax, where the target, the neutrophil, also expresses the same target as senescent cells. So navitoclax can kill neutrophil also. So what we are using here is it's a new class called prodrugs, which has basically a drug that is not active unless there is a trigger or a key that turns it on. And so in this case, the cells that we want to target needs to have not only the target molecule for the drug, but also the trigger. So it's like a double identification system for if you want to log into a website. You need not only to have a passcode, but you need the code that is sent you on your phone to verify again that it's you. Right. So this double verification system for targeting senescent cells definitely will increase the safety of the molecule that we are using, and hopefully also the benefits in the treatment.
So some non-senescent cells might have the metabolic marker that the drug targets, but because they don't have the trigger, those cells will not be affected by the drug. Yes. On the other hand, some might have the trigger situation, but they don't have the metabolic marker, so they will be left behind. And so the result is, at least conceptually, you should have the ability to leave a lot more non-senescent cells behind while still destroying high levels of senescent cells. Yeah. And you've already tested a few of these prodrugs. What have been the strengths and limitations of those?
Yeah, definitely they are very good, actually, in vitro at least. We tested one of them. It works.
Meaning with cells in a dish.
Yeah, in a dish, yes. it works very well. But when we tried it, we did some preliminary toxicity studies in mice. It looks like it's not as we really wish for. There is some level of toxicity there, so we want to improve in that. And for that reason, we would like to, we are actually developing our own prodrug that is not based on the same mechanism as the second generation prodrug. The second generation prodrug that we use, they are based on an enzyme called senescence associated beta-galactosidase.
These are the ones you've already tested.
Yeah, that's the trigger. But that trigger, although senescence associated beta-galactosidase is known to be a marker for senescence, everybody agree that it's not really very reliable and it's not expressed in all senescence cells. So we want to use a novel prodrug class that do not use senescence beta-galactosidase. It uses another key characteristic of senescence cells that is very promising. Yeah.
And this is a characteristic that's been discovered by Dr. Adamasu, who is also working here at SENS Research Foundation. And I know you can't say too much about that because it's not published yet. But as a general thing, you have this new prodrug approach where we can more selectively target senescent cells based on something that we think is going to be much more selective.
Yes, absolutely. Yeah, and hopefully it will be safer also. Yeah, so we have some preliminary data that is very promising. So that makes it more confident that it may work. Yeah.
Great. Okay, and then you are complementing this with mesenchymal stem cells. And tell us a bit about what historically has been the thoughts around mesenchymal stem cells and what we know about them now, and why it makes sense to combine those two therapies together in this context.
Yeah. Mesenchymal stem cells is a type of cells, stem cells that are found in adult tissues, and they are believed to be able to differentiate. And actually, there is data that shows that they can differentiate in different cell types.
So, meaning they start off as mesenchymal stem cells, but at least in principle, they can become muscle cells or fat cells or any number of different kinds.
Yes. In the dish, yeah. But so they were that was the rationale for using them as therapy for replacement, cell replacement therapy for various chronic diseases, and they show some beneficial effects. But however, the mechanism, really how they work, is not clear, and there's a lot of work recently trying to figure out how that works. And initial belief was that they will just go and differentiate and replace these damaged cells. But the data for that was kind of scarce, and it was found actually the belief right now and the consensus is that actually they act not directly by replacing cells, but just secreting factors that instruct cells, the healthy cells, to fight or to repair the damage, or to instruct other progenitor cells in that area to differentiate and replace this, but not the one that we inject, the one that goes there. Right. They may instruct others that they are already there to differentiate and help in fixing the damage. Yeah.
But they have limitations in their ability to do all those things. So in terms of both reaching the site of the damage, sustaining there, and producing those factors. So can you talk about those limitations?
True. It has been shown that actually, if you inject mesenchymal stem cells to the mice, they don't live more than 1 week. Mm-hmm. So and also we don't know whether during that week whether they're still functional or not, whether they secrete the therapeutic secretome or not. Right. So we are trying to verify this characteristic before even we try to inject them. We did a lot of work in vitro to try to see how we can make them survive, how we can increase the survival pathways, how we can check their secretome is there and it's still working. And then we inject them into the mice and we validate these things and see if our projection or our testing in vitro, whether it's confirmed in vivo. The goal is to make them live in mice more than a week, like maybe 2 or 3 weeks or more, and still functional. And if we do that should improve the therapeutic effect of these cells.
And what is the advantage of combining the mesenchymal stem cells with the senolytic drugs? Why are those two a logical complement?
Yeah, definitely. The field is right now moving toward combination therapies for many reasons. But one of them is that removing senescent cells themselves, it's good, but it may not be enough because senescent cells are generated continuously. So we need either to find a way to time the frequency of the treatment of the senolytics, so we can keep always the level of senescent cells as low as possible, or try to intervene in somewhere in the path that lead to senescent cells, so we can delay their generation. I think combining both will be even much better.
Right, and mesenchymal stem cells might plausibly do that because they have the anti-inflammatory effects, and we know that one way that senescent cells can spread is through these inflammatory factors that are released by other senescent cells.
Yes.
So you might interrupt that cycle.
Yes, they can do that too. Yeah, they can definitely either instruct other cells, progenitor cells, to enrich the tissue in functional cells, so they will diminish the harmful effect of senescent cells, or they may just secrete, as you said, molecules that counteract the harmful effect of senescent cells straight, directly. Yeah.
Right, great. Okay, we've talked about the limitations that MSCs have, and we've talked about how you are going to improve on their function, and we've talked about the new set of prodrugs that you're using. I think we are close to the end of the essence of this, so I will just wish you good luck and Godspeed.
Thank you for having me. Thanks so much.